If you take two standard flashlights into a dark room and cross their beams, they just pass right through each other. In open space, light beams act a bit like ghosts. The light from one flashlight doesn't push, pull, or bounce off the light from the other. They simply don't interact. If we actually want light to affect other light, we need a middleman. We have to send those beams through a physical material, like a block of glass, which is made of atomic structures. Imagine the atoms inside the glass as heavy weights, held together by elastic springs. When everyday light enters, it gives these springs a gentle tap. They hum in a smooth, even rhythm, passing the light exactly as it entered. Because everyday light is relatively weak, the springs handle it easily. The light exits the glass with the exact same color and shape. Physicists call this predictable behavior linear optics. In 1960, scientists successfully turned on the very first working laser. A laser doesn't produce a soft glow like a flashlight. It fires a highly concentrated, incredibly intense blast of pure energy. When you shoot a laser into our glass, it doesn't just tap the atomic springs, it yanks them to their absolute limits. Unable to handle the load, the springs warp, stretch too far, and snap back violently. The smooth rhythm breaks down entirely. By forcing the atoms into this chaotic state, the laser alters the physical properties of the glass itself. This brings us into the strange world of nonlinear optics. Because the atomic springs are now snapping back so erratically, they start throwing off light at entirely different speeds than the light that went in. If you shine an invisible, slow-moving beam of infrared light into the crystal, it yanks the springs so hard that they snap back twice as fast. Out the other side comes a fast, visible green light. Physicists call this process frequency doubling. If you've ever used a green laser pointer, you've held this exact process in your hand. An invisible beam inside the laser pointer is being doubled into green light before it hits the wall. We can see this in the documentation from the first time scientists pulled this off. This diagram shows their exact setup: an early ruby laser firing into a quartz crystal, forcing the crystal to output a completely new color of light. The crystal can perform another trick too. If a laser pulse hits the atoms with enough force, it can shove them entirely to one side and hold them firmly in place, stopping the vibration. By freezing the atoms in this compressed position, the energy of the moving light wave is transformed into a steady, continuous stream of electricity. Which brings us back to our two flashlights in the dark. If standard light beams act like ghosts passing right through each other, what happens if we fire two intense lasers so they cross inside our block of glass? Laser A hits the glass first. It blasts into the atomic springs, stretches them to their limit, and holds them in a tight, warped shape. When laser B tries to cross that exact same spot, it doesn't pass through an empty space. It hits a physical roadblock. The atoms have been stretched and stiffened by the first beam. By altering the glass itself, laser A successfully bends, blocks, or alters laser B. We are finally using light to control other light. Because one beam can block or redirect another, light can act as a physical switch. We can use a steady laser to instantly flip another signal on or off. This allows us to route data without having to convert it back into slower electrical signals. Using light to control light means information can be redirected while maintaining its native speed. This principle is a key part of the global fiber optic networks that carry our internet data today. By learning to push atomic springs to their physical limits, scientists moved beyond simple reflection. They discovered how to use the materials around us to shape light into an active tool that helps build our digital world.